Sometime in 1943, a German engineer at an aeronautical facility inside the Third Reich was handed something unusual: a Pratt Whitney R-2800, a twin-row, 18-cylinder radial aircraft engine recovered from a downed American aircraft. He was asked to examine it, assess it, and report back. He began with the casings. The two halves of the crankcase that formed the engine's structural core were machined surfaces that had to fit together with enough precision to seal oil inside the engine under high pressure and high temperature. Every aero engine he had worked with required a gasket between those two mating surfaces, a strip of sealing material, usually copper or a composite, that compensated for the microscopic irregularities in the machined faces and prevented the high-pressure oil inside the engine from finding its way out. He looked at the American crankcase. He looked at both mating faces. Then he put them together without a gasket, the way you might put together two surfaces that didn't need one, just to see. They sealed, without any gasket. The faces were machined to such precision that they simply fit, metal to metal, tight enough to hold oil under full operating pressure without any compensating material between them. He sat with that for a while. Then he wrote something in his report that his superiors did not want to read. He said, and different versions of the account use slightly different words, but the substance is consistent, that if this was what American industry could mass produce, the war was already lost. He was not a defeatist, he was an engineer. And what he had just held in his hands was not simply a well-made component, it was the physical proof of something he had not believed possible until that moment, that the Americans were producing, in quantity, on moving production lines, with workers who had been civilians 18 months earlier, a standard of precision that German manufacturing associated with handwork, with specialists, with the kind of painstaking individual attention that mass production was supposed to make unnecessary. It was not simply that the Americans had built a good engine, they had built a good engine that could be reproduced identically, at scale, in enormous numbers, by an industrial system that had been building refrigerators and automobiles 3 years earlier, and then turned itself, almost overnight, into the largest military production enterprise in the history of the world. The engineer's conclusion was not pessimism, it was arithmetic. And the arithmetic was correct.
To understand what was inside that engine and why it mattered so much, you first have to understand what the Germans thought they were getting when they recovered it. By the middle of 1943, captured American aircraft were turning up at German test facilities with increasing regularity. American bomber formations were flying over occupied Europe in unprecedented numbers, taking losses that were, for a period, appalling. Raids over heavily defended targets like the ball bearing plants at Schweinfurt were costing entire groups of aircraft and their crews, and the wreckage of downed machines was being systematically collected, examined, and in some cases rebuilt and test flown by German technical intelligence personnel. A network of salvage units called Bergbataillone combed crash sites across occupied territory, racing against Allied fighter bombers that would strafe the wreckage if they spotted it, to recover anything useful before it was destroyed or too badly damaged to yield information. The aircraft they were most interested in were fighters. Germany's defense depended on intercepting American and British bomber formations, and the quality of the fighters flying escort with those formations was a direct operational concern. The American fighter that appeared in German skies in increasing numbers from early 1943 onward, the Republic P-47 Thunderbolt, was enormous by the standards of the period. Where German fighters were lean, refined, carefully optimized machines built around the premise that combat performance demanded the minimum possible weight and frontal area, the P-47 was massive. It weighed nearly 7 tons fully loaded. It was powered by an engine the size of a small automobile. Its cockpit was spacious enough that a pilot could practically stand up inside it. By the aesthetic standards of German aviation engineering culture, it looked crude. Not crude in the sense of badly made, crude in the sense of unsophisticated, blunt, inelegant. A machine designed by people who had solved engineering problems with size and power rather than precision and finesse. On the 10th of November, 1943, a German test pilot named Hauptmann Hans-Werner Lerche climbed into the cockpit of a captured P-47 at the Airprobungsstelle Rechlin, the Luftwaffe's main test and evaluation facility, and took off. Rechlin was the place where German aviation sent everything that mattered, everything new, everything that needed professional evaluation. It was staffed with among the best test pilots and engineers the German aviation industry had produced. If anyone could assess what the Americans had actually built, it was the people at Rechlin. Lerche flew the P-47 for 90 minutes. When he landed, he sat down and wrote his assessment. And what he wrote contradicted the intelligence briefings in almost every particular. The Americans had not built a crude aircraft, they had built a practical one. And the difference between those two descriptions, crude versus practical, was a difference that went to the heart of what the two aviation industries had been trying to accomplish and which one had actually succeeded. Lerche's report on the P-47 was the kind of document that institutions sometimes produce when an individual inside them has decided to tell the truth about something the institution would prefer not to hear. He worked through the aircraft systematically. The cockpit, which from the outside looked oversized and ungainly by German standards, turned out to have been sized deliberately. The P-47 was designed to fly escort missions of 8 hours and more, following heavy bombers all the way across Europe and back, and the cockpit size reflected this. A pilot who had been in a cramped German fighter cockpit for 4 hours was a pilot whose attention had been degrading for the last 90 minutes from fatigue and discomfort. A pilot in a P-47's cockpit after 4 hours was, comparatively, still fresh. The size was not a failure of German-style minimalism, it was a design choice, deliberately made in favor of the human being who would have to function inside it for most of a day. The instruments were color-coded and simplified, designed, as Lerche noted, to allow pilots who had minimal training time to fly safely. This was not, as the briefings had implied, a concession to American pilots' supposed technical inferiority. It was an acknowledgment that the American military was training aviators at a rate Germany could not approach, and that instruments needed to work for those pilots quickly, intuitively, under stress, without the years of experience that German pilots brought to interpreting more complex displays. The construction was robust beyond anything German fighters typically achieved. The P-47 was built to absorb damage that would have been fatal to lighter, more refined aircraft. It came home from engagements that should have ended it. Luftwaffe ace Heinz Baer, who faced the P-47 in combat multiple times, described it afterward as absorbing an astounding amount of hits and requiring very careful handling to bring down. This was not accident or over-engineering, it was a specific design priority, chosen because an aircraft that returns to base, is repaired, and flies again the next day is more valuable over the course of a campaign than an aircraft that performs marginally better per mission but is lost at a higher rate. Lerche's report wrote that the P-47 was a practical aircraft. In the vocabulary of an aviation engineer, practical is a complex word. It means the aircraft does what it is designed to do for the people who will fly it, in the conditions they will actually encounter, at the scale it will actually be produced. By that standard, not the standard of what a single handcrafted prototype could achieve in ideal conditions, but the standard of what a mass production aircraft could deliver consistently across thousands of units, flown by thousands of pilots in every kind of weather and every kind of combat, the P-47 was not inferior to German fighters. In important respects, it was superior. Lerche's report would have been useful if it had been taken seriously.
The institutional response was to file it and continue with the existing assessment. The intelligence briefings did not change. The assumption of American technical inferiority was too embedded in the culture of the German aviation establishment and too politically convenient for a leadership that required its people to believe in German superiority to be revised on the basis of one honest test pilot's 90-minute flight. But in the engineering workshops, separate from the propaganda, the engineers who had the engines in front of them were arriving at their own conclusions. The R-2800 Double Wasp was Pratt Whitney's masterpiece, and by the time Germany was examining recovered examples of it, it had become one of the most important aero engines in the world. It was an 18-cylinder twin-row radial engine, 2 rings of 9 cylinders each, arranged around a central crankcase, air-cooled, producing somewhere between 2,000 and 2,400 horsepower depending on the variant and the fuel. It was America's first 18-cylinder radial, and it was smaller in displacement than the only comparable design from another nation, a French engine called the Gnome Rhone 18L, while being significantly more powerful. This feat of engineering was partly a matter of design and partly a matter of the manufacturing precision that allowed the engine to run at higher pressures and higher temperatures than less precisely made equivalents could sustain. The engine had a specific cooling problem that the designers had solved in a way that told you something important about how Pratt & Whitney approached manufacturing. Radial engines are air-cooled. Rather than circulating liquid coolant through the engine block the way a car engine does, they rely on airflow over the outside of the cylinders to keep temperatures within limits. This means the cylinder heads need fins, thin flanges of metal that stick out from the surface, multiplying the area available for heat transfer. Every other manufacturer of comparable engines at the time cast or forged those fins onto the cylinder head, which was cheaper and faster, but limited how thin and how closely spaced the fins could be. Pratt & Whitney machined their fins from the solid metal of the cylinder head forging. A gang of milling saws, automatically guided, cut every fin simultaneously in a single pass, producing fins that were thinner, more closely pitched, and more consistent than cast or forged fins could ever be. The process was more expensive. It was also more precise, and the precision produced more efficient cooling, which allowed the engine to run at higher power outputs than its competitors. The crankcase was the detail that stopped the German engineer cold. A crankcase is the structural housing that contains the crankshaft, the rotating component that converts the up and down motion of the pistons into rotational power. It is typically split into 2 halves for assembly reasons, and those 2 halves have to join along a flat mating surface. That surface has to be sealed against oil pressure. In every aero engine the German engineer had worked with, including the excellent German engines of the period, including the BMW 801 and the Daimler-Benz liquid-cooled engines that powered some of the finest fighters of the war, that seal was achieved with a gasket. The gasket compensated for the microscopic surface irregularities that any machined surface, however carefully produced, would have. Even the 2 halves of the crankcase were machined to such flatness, the process was called lapping, the grinding of 2 surfaces against each other until they were as close to perfectly planar as the process could achieve, that they sealed without any compensating material, metal to metal, no leak. Not even oil, which at operating temperature and pressure was a demanding test of any seal, found a way through. The German engineer understood immediately what he was looking at. This was not a tolerance achievable by hand-fitting, by skilled craftsmen spending hours on a single component. It was not the work of a specialist at a bench. It was the output of a production line that had been designed, from the machine tools to the measuring instruments to the process sequence, to achieve this standard automatically on every unit without special attention. It was mass production that had been refined past the point where mass production was supposed to be able to go. If that is what the Americans can mass produce, he said, the war is already lost. This is the moment this story has been building toward, and it is the right moment to stop and ask you to subscribe, because what comes next is where the engineering explanation turns into something much larger. The crankcase was not just a component, it was the evidence of a decision and a system and a history that went back decades. Subscribe before we go there, because the rest of this story is where it gets genuinely remarkable. The precision in that crankcase did not appear from nowhere. It was the product of a specific industrial tradition that America had been building for 100 years, and that had reached maturity just in time to be applied to aero engine production at exactly the scale the war demanded. The tradition began with what historians of manufacturing call the American system of production, the interchangeable parts manufacturing philosophy that had been developed in American armories in the early 19th century, refined through the Civil War, and then applied to civilian manufacturing in the decades that followed. The core idea was radical in its original context and is so familiar today that it barely registers. Components should be made to such consistent specifications that any instance of a part can be used in place of any other instance of the same part without fitting, adjustment, or selection. Interchangeable parts. The implications of this idea, compounded over a century of refinement, were exactly what the German engineer was looking at in 1943. Interchangeable parts require consistent manufacturing. Consistent manufacturing requires precise machine tools. Precise machine tools require measurement standards that are consistent, universal, and accurate enough to verify that the parts actually meet the specification. By the time the United States entered the Second World War, American industry had a machine tool industry, a measurement standard system, and a manufacturing culture that had been optimizing for this kind of consistency for generations. The automobile industry, Ford, General Motors, Chrysler, had taken the interchangeable parts system and pushed it to extremes that no one in 1850 could have imagined. The machines that made cars were themselves products of that precision tradition, and those machines, and the people who ran them, and the engineers who designed the production processes, all came into the war economy essentially intact, immediately available. The specific tool that made the R-2800's crankcase flanges possible was not a dramatic invention. It was a refinement of machining and surface grinding technology that had been continuously improving in American machine tool shops since the 1920s. The companies that made those machines, companies in Cincinnati and Cleveland and Detroit and Springfield, Massachusetts, were making them better every year in ways that pushed the achievable tolerance closer and closer to the physical limit. By 1943, the achievable precision in a high-quality American manufacturing operation was genuinely different from what was achievable in German manufacturing. Not because German engineers and machinists were less skilled, but because the American machine tool industry had spent more years optimizing for precision as a primary design criterion. Germany had excellent engineers. It had excellent machinists. What it did not have was an industrial system that had spent a century optimizing for the specific combination of precision and scale that American manufacturing had achieved. German precision manufacturing was associated with handwork, with specialists, with the Meister tradition, the master craftsman whose skill could achieve things machines could not. American precision manufacturing was associated with machines that could achieve, automatically and consistently, things that only specialists could do by hand. The war was, among many other things, a competition between those two traditions, and the crankcase was the moment that competition became visible. There was a second thing the German engineers discovered when they examined American aircraft engines, and this one was in some ways even more disturbing than the crankcase, because it was not something they could address simply by improving their manufacturing. American engines ran on 100-octane aviation fuel. Some late-war American aircraft ran on 130-octane fuel, and certain versions of the R-2800 were cleared for 150-octane fuel in emergency combat conditions. German aviation fueled its aircraft primarily on B4 fuel, roughly equivalent to 87 octane, with high performance variants on C3 fuel, roughly 91 to 100 octane, available only to certain aircraft in certain conditions. Octane rating is a measure of a fuel's resistance to detonation, the tendency of fuel to ignite prematurely under pressure before the spark plug fires, in a way that produces a sharp, damaging knock inside the cylinder, rather than the smooth, controlled burn that an engine is designed to use. Higher octane fuel gives you more headroom before you hit that limit. It lets you push harder for the same risk of damage. The practical consequence for the P-47 and for other American aircraft running 100 octane and higher fuels was that the same engine produced measurably more power than it did on German-grade fuel. When German test pilots flew captured P-47s on German fuel, they were flying an aircraft that was producing less power than the same aircraft produced in American service. When German engineers compared performance figures from American technical documents with the performance they were measuring at Rechlin, they found discrepancies that initially seemed like documentation errors. The American figures were simply higher than what the German tests were reproducing. The fuel explained the discrepancy. But the fuel was not just a technical detail. It was the product of a decision made by the United States government mining processes, different chemical additives, different quality control throughout the distribution chain. The man most responsible for the development and distribution of 100-octane aviation fuel to American and Allied forces was an unlikely figure for such a consequential role. Jimmy Doolittle, who would later become famous for leading the raid on Tokyo, had spent the early 1930s working for Shell Oil, where he had championed both the development of high-octane fuel and the design of aircraft engines capable of taking advantage of it. The infrastructure he helped build, the refining capacity, the distribution network, the standardized fuel specification, was one of the things that made the American aviation war effort possible at the scale it reached. The Germans understood, when they worked out what the fuel difference meant, that they were not simply looking at a component gap that better engineering could close. They were looking at a systemic advantage, a fuel supply chain of a quality that German industry under wartime conditions, with its oil supply increasingly disrupted by Allied bombing, could not match. The C3 fuel was not widely available. The aircraft that most needed it, the high-performance fighters defending the Reich, were not always getting it, and the aircraft they were defending against were routinely running on fuel that gave their engines an inherent power advantage. In the spring of 1943, the head of German military intelligence, Admiral Wilhelm Canaris, received a report from multiple independent sources about an American aircraft factory in the state of Michigan called Willow Run. The report said the factory was producing complete B-24 Liberator bombers at the rate of 1 per hour. Canaris's officers checked the figures 3 times. They remained unchanged. The B-24 had more than 1 million individual parts. It was one of the most complex manufacturing objects in the world. 1 per hour. The German leadership's first response was disbelief. The figures were assumed to be American propaganda, or to represent some deliberate exaggeration intended to intimidate. A bomber every hour was not plausible. The B-24 was the same aircraft that German industry, with all the accumulated expertise of a military aviation industry that had been building sophisticated aircraft continuously since the early 1930s, could not have conceived of producing at anything approaching that rate. What the German leadership was refusing to believe was the consequence of something they had consistently underestimated about the American industrial mobilization. The extent to which the same techniques that had made American automobile manufacturing the most productive in the world could be applied to the manufacture of far more complex objects. Willow Run was a Ford plant. It had been designed by Albert Kahn, the same architect who had designed Ford's River Rouge complex in the 1920s, the plant that had set the standard for integrated industrial production in automotive manufacturing. The people running it were Ford engineers and Ford production managers who brought to bomber production the same philosophy that had produced 15 million Model Ts.
Design the process, standardize the components, divide the work, keep the line moving. The plant was 1.5 miles long. It was so large that clouds sometimes formed under the roof. 40,000 workers, including women and people who had never worked in manufacturing before the war, assembled bombers on a moving line, the same moving line principle Ford had used for cars, applied to aircraft that weighed tens of thousands of pounds and contained more than 1 million parts. Each worker performed one specific task repeatedly until it could be done in the minimum possible time with the minimum possible error. The aircraft moved down the line, the workers stayed in place. The components arrived in sequence from suppliers whose own operations had been designed to produce them in exactly the right form for installation on the moving line at exactly the right time to keep the line from stopping. The intelligence officer who had lived in the United States before the war and understood what he was looking at wrote a private assessment that mirrored what the German engineer had said about the crankcase. If the data were accurate, Germany had already lost. It was only a matter of time and mathematics. Albert Speer, who ran Germany's armaments production, understood this as well. His private notes acknowledged that even if half the reported production figures were accurate, Germany faced destruction of its industrial base before its own production could recover. He understood. He could not say so publicly. Truth had become treason, and the leadership that needed to hear it was the least able to receive it. The Willow Run plant produced, across the course of the war, more than 8,000 B-24 Liberator bombers. The engine inside each one of those bombers was the R-2800. The crankcase in each one of those R-2800s was machined to the same tolerance, every one of them sealed without a gasket. If the story of what was inside the engine and what the engine's existence revealed about the industrial system that produced it is the kind of history that makes you see the war differently, subscribe now. That is genuinely the whole reason this channel exists. Because the next part of the story is about what Germany tried to do about all of this and why it was already too late.
The German aviation industry was not passive in the face of what it was discovering from captured American equipment. It had engineers of genuine brilliance, the best aeronautical research facilities in the world, and a tradition of technical excellence that had produced some of the most advanced aircraft of the era. The question was not whether Germany could build excellent aircraft. It had already demonstrated, repeatedly, that it could. The question was whether any of that excellence could address the specific problem the crankcase represented. The problem was not a design problem. German designers could look at the R-2800 and understand it, could appreciate the engineering choices behind it, could in principle produce designs of equivalent or superior quality. The BMW 801, the primary radial engine used by German fighters, was a capable and well-designed 14-cylinder radial that powered the Focke-Wulf 190, one of the finest fighter aircraft of the war. The Daimler-Benz liquid-cooled engines were extraordinarily refined, producing some of the highest specific power outputs of any engine of the period through elegant engineering and careful metallurgy. The problem was a manufacturing problem. Germany's precision manufacturing capacity was real, but not scalable in the way that American manufacturing had become scalable. The handwork, the specialist skills, the master craftsman tradition that German manufacturing was built on were not replicable at American rates. You could not take a BMW engine worker and make him a Pratt Whitney production worker, because the BMW engine worker's value was in specific knowledge and specific skill that had taken years to develop, and the American production worker's value was in the reliability and precision of the machines he was operating, machines that had been designed to do the precision work automatically, without depending on individual skill. Germany tried to address this through innovation. The turbojet engine, which Germany developed further and earlier than any other nation, was a potential path around the piston engine's limitations. A jet-powered aircraft did not need the same manufacturing precision in its power plant that a radial piston engine demanded, and German jets in 1944 and 1945 were capable of speeds that no propeller-driven American aircraft could approach. The Me-262, the world's first operational jet fighter, flew faster than anything the Americans had in the air. In individual aerial encounters, it was dominant. But individual aerial encounters were not what decided the air war over Europe. What decided the air war was the ratio of aircraft produced to aircraft destroyed, sustained across months and years of operations. The Me-262, for all its performance superiority in a straight comparison, was produced in a quantity that never approached the scale of American piston engine production. The factories that made it were bombed. The fuel it required, synthetic aviation fuel, which Germany was producing from coal in a process that itself was a target of Allied strategic bombing, was being destroyed at the source. The pilots who flew it were being killed in engagements in which the Americans, unable to catch the 262 in a straight fight, had figured out that the critical vulnerability was the landing approach, when the jet slowed to piston engine speeds and became briefly catchable. German technical ingenuity was genuine. The F-0, the first American operational jet, was influenced by German jet engine technology acquired at the end of the war. The swept wing research that German aeronautical engineers had been conducting at centers like the Deutsche Versuchsanstalt für Luftfahrt became the foundation for post-war jet aircraft design on both sides of the Cold War. The technology was real. What it could not overcome, inside the time available, was the gap between what German manufacturing could produce and what American manufacturing was already producing at scale.
It is worth stopping here and simply looking at the numbers, because the numbers are where the story becomes most stark. At the beginning of the war, Pratt & Whitney was producing approximately 5,000 aero engines per year. By the end of the war, the company was producing 50,000 per year, a tenfold increase in output, achieved while simultaneously increasing the sophistication and performance of the engines being produced. The R-2800 that began the war producing 2,000 horsepower ended it producing 2,800 horsepower in standard configuration, with emergency ratings approaching 3,400 horsepower using water injection. Same basic engine family, more power, 10 times the production volume. Pratt & Whitney did not do this alone. Ford's Buick division received a contract to produce 500 R-2800 engines per month. The contract was doubled, then doubled again. By 1944, the Buick plant in Melrose Park in Michigan was producing 2,000 R-2800 engines per month. Buick, the automobile company, making the same engine to the same tolerances, producing the same ungasketed crankcase seal at industrial volume. This was the element the German engineers' report was capturing. It was not that Pratt & Whitney had managed to produce one crankcase to this standard. It was that Ford's Buick division, a car company staffed by people who had been making sedans 18 months earlier, was producing 2,000 of them per month, and each one met the same specification, and each one sealed without a gasket. The tolerance was not a special achievement, it was a minimum acceptable standard that every unit had to meet before it was installed in an engine, and every unit did. Across the entire American aero engine industry, Pratt & Whitney, Wright Aeronautical, Allison, Lycoming, and Continental, the United States produced more than 800,000 aircraft engines during the war. More than 800,000. The British and American Air Forces operated on those engines across every theater of the war simultaneously, from the Pacific to North Africa to Western Europe, and the engines were available in the quantities required because the factories that made them were producing at rates that no other nation and no previous era in the history of manufacturing had approached. Germany produced in total approximately 200,000 aero engines during the war, superior in many individual respects, adequate to equip a smaller air force with sophisticated aircraft, wholly insufficient to match what the other side was producing. This is the context in which to understand what the German engineer held in his hands when he put the two crankcase halves together without a gasket. He was not looking at the product of a superior engineering culture. He was looking at the product of a superior manufacturing system, a system that had been building precision at scale for 100 years, and that had then, in the space of 3 years, applied that precision to the most sophisticated and demanding manufacturing challenge of the century, and had done it at volumes that were, in the most literal sense, incredible to anyone who had not seen them with their own eyes. Let's take a moment and make sure we have the full picture, because the final acts of this story bring us to the question that the crankcase ultimately poses, not just about the war, but about how industrial advantage actually works and what it takes to build the kind of system that produced that seal.
There is a temptation when telling the story of American industrial production in the Second World War to present it as a simple triumph: more factories, more money, more resources, and therefore more victory. And while the resources were genuinely decisive, the story of the crankcase suggests that what resources bought was more specific than that. What American industrial production achieved was not simply more, it was more precise, it was more consistent, it was more reliably interchangeable. The parts that came off the production line at Pratt Whitney's Hartford plant and the parts that came off the Buick plant in Michigan were interchangeable. Not approximately interchangeable, not interchangeable within a range that required judgment to navigate, but interchangeable in the strict engineering sense, meaning a part from one plant could be installed in an engine assembled at the other without selection, fitting, or adjustment. This interchangeability had an operational consequence that went beyond the factory floor. In the field, in the combat maintenance depots where damaged aircraft were repaired, an American mechanic working on a damaged R-2800 could reach into a parts bin, pull out a cylinder, and install it. He did not need to measure it against the engine it was going into. He did not need to select for fit. He pulled it out of the bin and put it in, and it worked, because it had been made to the same specification as the part it was replacing. A German mechanic working on a damaged BMW 801 might need to select among available parts, measuring against the specific engine being repaired, because the tolerances in German manufacturing, while tighter than many other nations, were not always tight enough to guarantee interchangeability without judgment. This added time to every repair, it added complexity, it added a dependency on skilled mechanics that became increasingly difficult to sustain as the war went on and losses accumulated. The interchangeability that the crankcase represented was not simply an engineering achievement, it was an operational multiplier. It meant that each aircraft, once built, could be maintained more quickly and returned to service more reliably. It meant that the 63 minutes for B-24 at Willow Run was not the end of the productivity advantage. It continued at every maintenance depot for the operational life of every aircraft the factory produced. This is what is genuinely difficult to convey about the American industrial achievement in the Second World War, because it does not reduce to a single dramatic moment or a single dramatic number. It is an accumulation of small precisions, the crankcase flatness, the fin machining, the cylinder head tolerances, the carburetor calibration, that individually seem like engineering details and collectively represent the difference between a system that works at scale and one that works in the workshop. The German engineering tradition excelled at the workshop. The American manufacturing tradition had learned to turn the workshop into the assembly line.
Think about what was in the engineer's hands when he put those two crankcase halves together. He was holding the output of 100 years of American manufacturing philosophy. Interchangeable parts, machine precision, production systems designed not for what a craftsman could achieve, but for what a machine could achieve consistently. He was holding the product of a decision made in a Hartford engineering office in 1937 to machine those fins from solid metal rather than casting them. He was holding the result of Jimmy Doolittle's work at Shell Oil in the 1930s, which had built a 100-octane fuel supply chain that gave every engine in American service a power advantage the fuel itself provided. He was holding something made by workers at a Buick plant in Michigan who had been building sedans 18 months earlier, and who were now on a moving production line producing this component to a tolerance that no gasket needed to compensate for. He held it together. It's sealed, metal to metal. And then he wrote his conclusion. Not because he wanted to, because he was an engineer, and engineers follow evidence, and the evidence in his hands was unambiguous. The war was going to be decided not in any single battle, not by the quality of any individual aircraft or pilot, but by the ratio between what each side's industry could produce and what the war was consuming. Germany's engineers were inferior to anything the Americans could put in the air. But Buick was making 2,000 R-2800s a month in Michigan. Willow Run was finishing a B-24 every 63 minutes. And every one of those crankcases sealed without a gasket. Not because a craftsman had hand-lapped each one to the required flatness, but because the machine that produced them had been designed to do so, automatically, at scale, to a standard that the American manufacturing system had spent a century getting to. The engineer was right. It was already a matter of arithmetic. And the arithmetic said that whatever happened in the air over Germany, whatever the quality of the machines and the courage of the men who flew them, the system producing those machines on one side of the equation could not be matched by the system producing them on the other. The gasket wasn't there. That was the story. That was the whole story. If the idea that a missing gasket can tell you who is going to win a world war is the kind of history that makes you see things differently, subscribe. That is genuinely the whole reason this channel exists.